Alright guys, so since the last video, I've gotten a lot of people who are just kind of frustrated and upset and send emails like, Boris, what's up with this might converge? You know, can we be able to conclusively determine whether something definitely converges or diverges? And today we're going to start to answer that question with something called the integral test. So the first thing I want you to do is to kind of make a little table, and you should put this somewhere in your notes so you can refer back to it a lot. And we're going to make a list of tests to determine whether a series converges or diverges. So we've already learned one, and I'm going to put that in here first. So inside this table, we're going to have kind of the name of the test, and then some hints on like when to use that test, and then kind of what are the results of that test. And then in our last lesson, we talked about the nth term test, or the series divergence test. And this is something you can always use, but the results are basically this. If you take the limit as n goes to infinity of that term, if that limit does not equal 0, the series diverges. And of course, the unfortunate part was if the limit of the terms did equal 0, it was not really conclusive. It didn't tell us anything one way or the other. And what we're going to learn about today, which is our brand new thing, is the integral test. So we're going to combine our love with series for our love for integrals. Okay, so when you can use this, that you should use the integral test if your function is easy to integrate. Okay, so and basically what this does, so basically we're comparing some kind of relationship between the integral and the infinite sum. And it basically just says this: if you take the integral from 1 to infinity of your terms, if that converges, then so does the sum. The sum from n equals 1 to infinity of a sub n. And then the opposite of this is true. This should be a dn, I'm sorry about that. The opposite of this is also true, that if you take that integral from 1 to infinity of a sub n, if that integral diverges, then so does the sum from 1 to infinity of a sub n. Now, this is exciting because in our last chapter, we learned how to do these infinite integrals. So if you get a number, you know the series converges. If you get infinity, you know the series diverges. So this could be like a really powerful test. So that's the integral test. Let's go ahead and put it to use in a couple cases here. First example here. We're going to go ahead and prove that the series from 1 to infinity of 1 over n actually diverges. So this, by the way, this is probably the most famous series that we'll see in this class. This is what's called the harmonic series because it has applications to music. But the harmonic series is the 1 plus 1/2 plus 1/3 plus 1/4. Okay, now if we had looked at this series from our prior lens, if you take the limit as n goes to infinity, you get 0. So it might converge. What we're going to do right now is use the integral test to prove that this series actually diverges. So what we do is we set up the integral test. So we say, all right, I'm going to take a look at the integral 1 to infinity of 1 over n. Now, we're all good boys and girls who get gifts from Santa, so we want to go ahead and write that as a limit as a goes to infinity of 1 to a. Okay, so that's going to become the natural log of n going from 1 to a, which of course is the limit of the natural log of a minus the natural log of 1. Now, when you take that limit, you get the ln of infinity minus 0, which is infinity. Okay, so the conclusion here, what you say is, since the integral test, since the integral here diverges, that means that the series also actually diverges. Okay, so that's the conclusion that you'll draw by doing the integral test. Let's take a look at another example where we're going to have to figure the answer out on our own. Okay, so let's take a look at the sum from 0 to infinity of e to the negative n. Okay, so if you want to take a look at this, well, again, let's just consider the integral. So let's consider the integral from 0 to infinity of e to the negative n dn. I'm not sure why I wrote a dn here. That was probably a mistake. Okay. So, if you want to have this series is like e to the 0 plus e to the negative 1 plus e to the negative 2 and so forth. So we're going to consider this. And again, the question that we're asking is this series a convergent series or a divergent series? Okay, so we're going to consider this infinite integral. So again, let's write it as a limit. I'll just put an x in there, I guess. Limit as x goes to infinity of integral 0 to x of e to the negative n. Okay, now we've done that integral a million times. You use a little u sub. It's negative e to the negative n going from 0 to x. We'll take that limit. So this is a limit as x goes to infinity of negative e to the negative x minus e to the negative 0. Okay, so as we take that limit, we end up getting negative 1 over e to the infinity. That's the negative exponent plus 1, which is just 0 plus 1, which is 1. Okay, now, the interesting part here with the integral test is that this number is irrelevant. It doesn't matter what this number is. It's not actually helpful to this. The important part is that we know that this integral actually converges. We get a number for the answer. And what that means then, of course, is that the series also must converge. Okay. So that's how the integral test works. If you get a number, you know the series converges. If you get infinity, you know the series diverges. Okay, so let's talk about just a couple caveats slash notes and tips to take advantage of with the integral test. The first thing, and this is kind of interesting, is your function must be a positive function. It must be a continuous function, so it doesn't have any like asymptotes in it. And it must actually be decreasing to use the integral test. And that's actually something they will ask about on the AP test and require you to write down on a free response. That if you're using the integral test, you got to say I have a positive, continuous, and decreasing function. Kind of it should have that general shape, kind of going down towards the axis for the integral test to work. Now, what's happening there, right? If we look at something like this, you know, these terms are all positive. These terms are getting smaller, right? 1/2, 1/3, 1/4. And then if we go from 1 to infinity, this function 1 over n is in fact a continuous function. So that's how we could use the integral test. But those are the three conditions. Okay, just a couple other notes to be aware of. Is just quick note, both the integral and the series may converge. But they're not necessarily equal to the same number. And in fact, they are almost never equal to the same number. I can only think of one real exception to that. So, for example, like we know that the series of 1 over n squared converges, and because we know that the integral from 1 to infinity of 1 over n squared converges. Now, if you do this integral like we did in the last chapter, we know this integral is 1. But if you took a look at the terms of this series, it's like 1 plus 1/4 plus 1/9 plus 1/16. Like this number is obviously like a number bigger than 1. If you're curious, this number it actually adds up to is pi squared over 6. That's not important. The important part is that these are different values. So they're not necessarily going to be the same value of the integral and the series. The integral test just tells you that if one converges, the other one converges. If one diverges, the other one diverges. Okay, so that's the integral test. Thanks for watching. In the next video, we're going to develop a very useful rule using this.